In this lesson, we're going to discuss the second type of improper integral. The first type of improper integral that we just saw in the last lessons were where the limits of integration were one or both were positive or negative infinity. So they were fairly easy to identify. It jumped off the page at you that you were dealing with an improper integral and that you needed to bring the limit to the party. And this type of improper integral, it's not necessarily going to jump off the page at you that you need to do that. You're going to have to pay attention, most especially when you have a rational function. When you have a fraction, you're going to have to pay attention that one of the values, either your left endpoint, your right endpoint, or some interior point on that interval, does not include a vertical asymptote. Here, clearly, if we have a value of x equal 1 and we're trying to do the fundamental theorem here and we're plugging in 1 for x, we've got an issue. This function is not defined when x equals 1. That means this function has a vertical asymptote at x equal 1. This function travels right alongside as input values get closer and closer and closer to 1 from the left. The output values go closer and closer and closer to bigger and bigger and bigger values. And depending on how closely over time that function travels right to the left of that vertical asymptote, in this context, that determines whether the area kind of sort of just quits getting bigger. And the closer and closer we get to 1 from the left, if not a lot of appreciable area is added to the area that's already being accumulated, then that's what convergence looks like. But if your function doesn't get close enough to its vertical asymptote, if area continues to be added and added and added onto there, that's what divergence looks like in this context. So we have to bring the limit to the party, because limits allow us to determine what's happening near. Right? That was the whole idea of nearness. And we don't have to worry about math issues at, right? Because we're near. Remember that idea. Here, this says we're getting very, very near input values of 1 to the left, but we're never at those input values. So you've got to bring the limit to the party, and it's not super, super obvious all the time when you have this type of improper integral, because that looks really innocent. You definitely have a well-defined left endpoint. You definitely have a well-defined right endpoint. So these improper integrals can kind of sneak up on you, so you need to pay attention. The biggest time they're going to show up, one of the main times they're going to show up, is if you have a rational function. If you have a fraction, then you might want to just stop and double check that you're not dealing with an improper integral. So let's see what this would look like. Let's see what the work would look like. Here, from 0 to 1, 1 over x dx. And this is a really good function for us to practice on, because it happens to be one that we know what the graph looks like. In quadrant 1, that's what the graph looks like. And so if we are integrating from 0 to 1, then we have bounded area on the right, but this value, that vertical line, is a vertical asymptote for this function. So depending on how closely, as we get closer and closer and closer to 0 from the right, depending on how closely that function follows along its vertical asymptote, this area may go ahead and converge, or if it doesn't get close enough, it may go ahead and diverge. So we have an issue at the left endpoint. Our interval that we're looking at on the real number line is the interval from 0 to 1. So we're going to introduce the limit, and we want the limit, this is the lower one, so I'll use the letter A. And we're going to approach 0. But are we approaching 0 from the left, or are we approaching 0 from the right in this interval? Here's our interval. Remember, you want to be inside your interval. We are approaching 0 from the right in this integral, right? It is our left endpoint on our interval, so we're going to approach input values from the right. So you need to make sure that on these intervals you are inside the interval when you're doing your calculus work. So there we are. Now I can evaluate this definite integral because I will never be at 0, so I don't have to worry about having trouble with that left endpoint. I'm only going to be near 0. So never drop your limit notation. It has to be there at every step. Find your antiderivative function. Announce to the AP reader you're going to do fundamental theorem, and then go about showing good steps to do that. So as we approach 0 from the right, we have the natural log of 1 minus the natural log of A. Now this interval, all the input values are positive, but if they weren't, if we were approaching some negative input value, then we would have the absolute value there, because remember, technically, that antiderivative is the natural log of the absolute value of x. Well, clearly here, we know the natural log of 1 is 0. So now, what is happening to the outputs? Remember, this is what limits ask. As inputs get near, and for us it would be as A approaches 0 from the right. So as inputs get near super tiny positive input values, what are outputs doing? That's what limits tell us. Well, again, we're really lucky here because this is a parent function and we know what it looks like in the plane. Let's graph it. It was one that way back in August we said we needed to make sure we knew how it behaved in the plane. And this is what the parent function of natural log looks like, right? It has one x-intercept, that's at x equal 1, and it has a vertical asymptote at x equals 0. So as input values approach 0 from the right, which is what our limit is asking, the output values are headed toward negative infinity. So this is infinity. Our original improper integral diverges. And there's the work that we would have to show in order to show that we see that it diverges. So there's your first improper integral with infinite interior points. Let's work another example. This one, again, it's a definite integral. It looks really innocent. It looks like we can just go about finding the antiderivative, which is going to be easy. That's a power rule. And we can go about doing fundamental theorem. But there's an issue. And the issue is not at 0, and the issue is not at 3. Where's the issue? This is not going to be defined. We're not going to have an output on this function at x equal 1. So here's an interior point where we have an issue. So what we're going to have to do is take this integral and break it up over that input value that's giving us trouble. Here we're going to approach the vertical asymptote from the left, but here we're going to have to approach the vertical asymptote from the right. We have to approach from, I think I said that backwards. Here we're approaching from the left. No, I said it right. And here we're approaching from the right because we have to be inside our interval. So the limit as b approaches 1 from the left, that's inside the interval, of the integral of 0 up to b of 1 over the quantity x minus 1 to the 2/3 dx, and that's going to be added to the limit as a approaches 1 from the right, that's inside the interval, from a up to 3 of 1 over x minus 1 to the 2/3 dx. So I'll do a different color over here. This is a u substitution where u is x minus 1, du is dx. Our indefinite integral is going to look like u to the negative 2/3 du. So with the power rule, 1 over n plus 1, that's 1 over 1/3, that gives us 3. U to the n plus 1, that's u to the 1/3 plus c. So there's our antiderivative function that we're going to use. Your notation has to be spot on here. Just because you know how to do the fundamentals and the meat of the processes, we don't want to lose any points because we got lazy on notation. So let's don't lose any points based on notation. Sorry, I don't know where I got 2 from. It's 1/3. And we're going to evaluate this one from 0 up to b. Then we have the limit as a approaches 1 from the right. Same antiderivative, but we need to show it here because we have 2 separate limits. You can't plop those in together. So now let's plug in our upper limit and our lower limit. B minus 1 minus 3 times 0 minus 1. There's fundamental theorem for this part. I'll drop down here. We're approaching here 1 from the right. And we're doing upper limit, we're plugging in 3. And lower limit, we're plugging in a. All right. So let's see what's going on here. So we're plugging in right here b values that are like 0.99999, right? Do you see that the result here is going to be super tiny, and negative? And remember, in the context of a limit, we get to say that goes to 0. So that's super tiny and negative, and we get to say it goes to 0. Here, we have negative 1 to the 1/3. That's a negative 1. So this is negative 3 times negative 1. So there's the first part, the limit as b approaches. Here, we have plus 3 times 2 to the 1/3. And here, we're plugging in 1.0000 a trillion zeros and 1. Something just a little bit bigger than 1. So if I have something a little bit bigger than 1 and take 1 out of it, this is super tiny and positive. And in the context of this limit, that term has a value of 0. So here's our result, and it's a finite real number value. This converges. That tells us that on both sides of the vertical asymptote for this function, that the function actually travels close enough to its vertical asymptote that as we get closer and closer and closer to 1 from the left, and closer and closer and closer to 1 as far as input values are concerned, the outputs of that function travel so close to that vertical asymptote that there's not a whole lot more area that gets added to the already accumulated sum. And that's what convergence for this type of an improper integral looks like. So one video for this lesson. Come to class next time and we'll do some homework problems.